Back to our next installment of the California Fire Seminar Series. My name is Michael Gollner from the University of California, Berkeley, and I'm here with Stacy Frederick from the California Fire Science Consortium. And today we are hosting two guest lecturers who are going to be talking to us today about the wildland urban interface. The first is Dr. Faraz Hedayati, and the second is Mr. Daniel Gorham, both of which work at the IBHS Research Center. And I've worked with both of them over a number of years. Both did their thesis work, Faraz on Embers in particular in the wildland urban interface, and Dan in wildfire spread. And IBHS has been really sort of a leader in the mitigation and hardening in communities. So we're really glad to have them present on both the capabilities and some of the hardening and other work and where it applies in the WUI. Before we get started, I just wanted to give you a little bit about the show today. So we have the question and answer on the bottom. If you have any questions, please put them in there and we will answer them at the end and call them out. We'll also record this for posting for anyone who wants to see. And Stacy has been doing wonderful organization and will continue to send out any updates as we have them for the next series, which will be going on about once per month through the summer. We're also soliciting for volunteers still, early career or students. If you'd like to get involved in planning or hosting some of these webinars, especially in California, but also welcome across the US, please get in touch. We have a survey. So now without further ado, Faraz and Dan, thank you so much for being with us today, and we look forward to your talk.
Hello everyone, and good to be with you.
And we are actually in a room together, which is not always the case. And so we're happy to do that. So we're using some of our technology here. So bear with us for just one more minute here, and then I will start with the slide deck. And thank you, Michael. Thank you, Stacy. Thank you, everyone, for the opportunity to speak with you today. As Michael mentioned, I'm Daniel Gorham. This is my colleague, Faraz. We're both research engineers here at the Insurance Institute for Business and Home Safety, IBHS. The photograph on the slide right now is our research center located in Richburg, South Carolina, about an hour south of Charlotte. And the why statement on the screen is the mission statement for our organization. So IBHS is a nonprofit organization. We are funded by the insurance industry, the property insurance industry. So we have members, including the primary insurers, the carriers, the reinsurers, the modelers of the insurance industry. So we don't work for any individual insurance company. They essentially all pool their funds and resources together to support the work that we do at IBHS. And that really looks at how do natural hazards and catastrophe events impact the built environment. We don't only look at wildfire, and in the next slide, I'll talk about some of those other weather phenomena that we look at. But really the mission of the organization is to look at severe weather, hurricanes, high winds, hailstorms, and wildfire, and their impact on the built environment. Faraz and I both come from a fire background, so we both primarily work in the fire space, which we're looking forward to talking to you about today. But the other work that IBHS does, high wind and real gusty wind is an important part that influences the work that we do in the wildfire space. And as I'm sure many of you are aware, the strong influence that wind has on fire behavior, and particularly in the built environment and fire spread, and Faraz will talk about some of that there. But with that, let me move along. And again, please, hopefully this video is not too choppy to kind of bring you into the research center. So this is the wall of fan, 105 fans, enough energy they consume to power about 9,000 homes. We can put a full-size structure inside there. In addition to the research that we do in the lab, we do field research, and this is looking at collecting hail from real hailstorms, recreating and simulating wildfire effects in the lab with wind speed and ember generators, wind-driven rain, as you typically see from a hurricane event, and how water can get into a structure, not just from the wind damage, but also the wind damage from high wind speeds, including hurricanes and other straight line winds like inland tornadoes. We look at both residential and commercial structures, different kinds of construction, whether it be wood frame or cement block, I think we're pretty famous for blowing down buildings and blowing roofs out of the backside of the chamber, like you saw there on that video. And, people look at IBHS and say, from the research perspective, from the physical science perspective, it's kind of like a big sandbox. And at least for me, that's the way I think of the research center. It's a great opportunity. What does Spider-Man's uncle said, with great power comes great responsibility. And we're able to do a lot of these things, but we take that, that opportunity seriously, and we want to move the needle forward. So that's what we're going to talk about for the rest of this presentation. Faraz and I both have our contact information. We're maybe not as active as Michael and others, but we're in the Twitter space if you want to contact us there. We also have our emails. And, just as a plug at the start of this presentation, this webinar, really our aim is to, to fuel or, spark the collaboration, to share what we're doing, to learn about what you all are working on, and find ways to make that connection go forward. So with that, I'm going to hand it over to Faraz.
Yep, thank you. Let me start by talking about Embers. So here is a video that you can see, probably have seen before, that we have, is from the 2016 fire in Canada. There are two different types of threats here from the fire. One is on the left-hand side of the image, which is like tall flames. The other one is spot ignitions near structures, right? So one can take the risk to live on either side of this street, basically, and be exposed to different threats. So when ember land near the structure, they ignite the recipient fuel, and that poses a small flame threat near the building. I like to look at the embers as particles, zero mass particles. And I talk about the difference here quickly. So these small particles can travel or will travel wherever the wind takes them, right? So they don't have any resistance basically against the wind patterns or the wind vortices. On the other side, embers do have mass, and they have some sort of resistance or inertia against the wind pattern or wind vortices. This photo is taken from back when Dr. Steve Coles was at IBHS, and this is like a great demonstration of the flow pattern near the structures, right? So we clearly see different types of embers. One is the heavier embers that when they hit the wall, they just fall, and we see that glowing line at the base of the wall. The other types of ember are the smaller embers or the lighter embers. When they hit the wall, they bounce back, and we see that glowing arc around the building, right? And the third one is basically the transition from 1 to 2. And that's when ember hang around at the base of the wall for a while. They lose enough mass that the wind vortices can push them back, and they go, and you see that the glowing lines from the base of the wall towards that glowing arc. So given this, we can understand why wind matters in ember accumulation near buildings. In other words, if we look at the energy distribution of wind or turbulence cascade, if we look at like an ember which is 2 millimeters long, right? If the wind vortex is like 10 miles, that wouldn't affect 10 miles wide, that wouldn't affect this specific ember, right? So on the other hand, if it's like in the same scale, that would change the location or the accumulation location near the building. So talking about wind, we can create constant wind fairly easy. We can increase the RPM and then measure the wind, and that's typically a straight line, as we can see here, and then we can interpolate that and then create any constant wind that we want with this information. In other words, contour volume of the of an air, like contour volume of air, when they leave the fans, they constantly move forward, and we can measure the wind speed. But when we interact with gusty wind, we need to combine different RPMs together, right? And that contour volume of the air, when that leaves the fan, it's not a constant velocity as it moves forward. It's basically as the RPM goes up, it pushes them forward, and as it slows down, it sucks them back. So we have this type of measurement. It's very noisy and very difficult to replicate. In addition to that, all fans have different RPM curves. In other words, if we want to increase the RPM by 200 RPMs, if we are at the lower end or higher end of the range of the fan capability, we need different power, right, or different time to get to that certain RPM. At IBHS, those threshold is 1,000, 1,500, and lastly 1,800. So we have different the RPM DT basically when we want to replicate the gusty wind. We measured the different velocities at different locations in our test chamber, and then put them all together, the velocity and their derivatives. And then we create a machine learning model. So basically the constant wind, we have a straight line, right? But here we need to model it stochastically. So that being said, this is what we could achieve. So Texas Tech University shares the data with us, and you see what they have measured over like 700 seconds, and the orange line or the red line is what we could create in the lab, right? It's fairly close. We can match all the peaks and the valleys and same energy distribution, which would basically affect the accumulation pattern near buildings. That being said, when we look at higher winds like Hurricane Florence, which is 70 miles an hour, right? So we miss a lot of the peaks and valleys here. The energy distribution is different, right? But we basically follow the same pattern. So in other words, the correlation is the same, but the magnitudes are different. And this is what I mentioned before about the RPM DT. As we go to higher RPMs, it gets more difficult for the fans or for the motors to replicate, to follow what models tells them to do. So with that, I want to talk a little about what we could see on the Embers side. So we talked about how we can create a realistic wind, any desired wind field, we can create that in the lab. So here is again from the experiment that Dr. Steve Coles ran a few years ago, maybe 2015. So we are looking down at Ember generators, and we have two control volumes. One is 10 feet from the building, and the other one is about 5. Our frame number, positive, negative, and total. So basically, if an ember is moving towards the building, that counts as positive. If it's going the other direction, which is 60 degrees or more, we count that as negative. Yep, there we go. Okay, so what we can see here is on control volume 1, almost all the embers are moving towards the house. On control volume 2, over time, we see about 40% of them are going back, which tells us the importance of these wind vortices near the structure. If we want to take action and basically harden the structure all the way for 100% of the embers, that would be probably over-engineering the problem. This is like just scratching the surface. We know that wind patterns are different when we have plants, when the surface roughness is different, which is on our to-do list for future. But this gives us an idea how can we attack this problem in parcel level. So to talk a bit more about a more complex wind field, which is the corner of the building, we see again the green arrows are the embers that are moving towards the house, and the red ones are the embers that are moving away, and basically out of that control volume. And in this case, it's more of like 70% of the embers do not hang around. They move, they are blown away by the small wind vortices near the buildings. We talked about embers, and this is like a bit about our current experiment, structure suppression experiments that we are collaborating with NIST, US Forest Service, Cal Fire. One big piece here was to measure the heat release rate of large sheds, and I will show you like some images after this. We engineered and built a very large mass loss platform, and you see the calibration curve there, actual mass versus measured mass. So we're talking about 9,000 kilograms, right? And the uncertainty in this measurement was about 50 kilograms. So that's pretty impressive when we talk about something around 40 load cells on the structure exposed to heat. So we had to isolate the load cells that we don't affect their accuracy based on the different temperature that they receive from the burning shed. And this is the heat release rate. So to my knowledge, this is the first time that we have, or by we I mean the community, have measured or estimated the heat release rate from different sheds. These two sheds are that have the same size. It's 12 by 24, I guess, and have the same fuel load. One of them is wood, the other one is metal. And we see how the heat release rate curves are different. One of them peaks and then dies down, and the other one peaks and it stays there for a while. And this could go in as like a source term in Navier Stokes equation to have that we can model the fire behavior better. And finally, we talked about the effects of wind. Play this, please. There we go. We talked about the effects of wind on heat release rate. Another way, one way is to look at mass loss. Another way is to look at fuel source term, basically. And we can see like how flame lengths and flame height are different at different wind speeds, and we can put them in the source model to understand the heat release rate and compare those to mass loss platform.
And so as Faraz was talking about some of the kind of technical aspects of, how we conduct the research and how important wind plays a role in ember transport and ember accumulation and fire behavior and that side of things, I'm going to kind of then take a step back from that and take that kind of fundamental foundational understanding of the physical phenomena and talk about how we have tested and how we think about buildings, right? The Insurance Institute for Business and Home Safety, homes and businesses are essentially buildings and structures, and how they're impacted by natural hazards. And in the wildfire sense, we think mostly that buildings are impacted by wildfires and that they are ignited. And if a building is ignited, it's most likely to be destroyed. Now, we don't have in this presentation, but we've done a little bit of work on non-destructive impacts of wildfire on buildings. An example of that might be smoke, right? Smoke might impact come into the building. Faraz talked about how smoke was essentially zero mass particles, so it can travel and be influenced by the wind. It can get in and around a structure and it might cause some smell damage. But putting that to the side, primarily we look at how do wildfires impact structures, that is, how do they ignite them? Faraz showed that image or that video from the Fort McMurray fire at the beginning, showing how we had this crown fire in the forest and how it was spreading up to the edge. There was some clearing of grass, there was the road width, and then there was the homes right there kind of at the edge of that wildland urban interface. And, we can think about the heat transfer and how do homes ignite, the first of which can be through radiant heat. So if we were very close to that crown fire, those trees, we would feel extremely high levels of radiant heat, probably so large that we couldn't be there with our bare skin. But radiant heat decreases exponentially with distance. And so the distance between the edge of those trees and the homes was enough, I don't know what it was, call it at least 50, 60 feet, was enough that the radiant heat wasn't enough to ignite things on the other side of the street. We also saw that the fire didn't spread. There wasn't continuous fire spread through the vegetation, right? There was the end of that tree line and there was some surface fuels, but at least in that part of the video, it hadn't spread along there. So there wasn't a continuous path of the wildland to the structure, but Faraz showed how the embers were able to transport over that distance, and they were able to ignite fuels like bushes, like firewood, like other things around the structure. We think about those embers igniting things around the structure, like the mulch on the ground that we see here, and the subsequent flames from that being attributed to as indirect ignitions of the structure. And they call it all that as a context to say, we talk about embers being the driving mechanisms for how wildland fires ignite structures. And we use a statistic up to 90% of homes are ignited from embers. And that is derived from thinking about both direct ember ignitions, and that say you had a wood shake roof and you have an ember landing on the wood shake and igniting it directly. That's a direct ember ignition. If say you have an open vent or an open window and an ember gets inside outside and you have combustibles in your attic or in your crawl space or an open window in your living room, and an ember ignites essentially the building directly or indirectly, because the ember ignites something, again, from that Fort McMurray fire, like shrub, or in a lot of the testing videos that we'll show here, maybe ignites debris underneath the deck and then the deck burns and taps the home, or it ignites this combustible mulch in the perimeter around the home, and then that subsequent flame ignites the structure. Those indirect ember ignitions is why we say the driving mechanism for building ignition is embers. All of that to then get back to what I'm going to talk about here is, thinking about the building, not just as individual components, the roof, the siding, the windows, the eaves, all of those things as a system. I'm going to show here over the next couple of slides some of those individual components, but really want to preface, and I'll reiterate at the end, the importance of thinking not just the roof vulnerability, but where the roof extends beyond the wall, which creates that eave, and you have something on the ground in that 5 feet, and you could have flames coming up from the ground up into that under eave area, right? That interface or that kind of intermingling of different building components, and really that being an important part of thinking about how are buildings susceptible to and how do buildings ignite, ultimately to get back to how do we build, how do we retrofit homes, parcels, and communities to be less susceptible, more resilient to wildfires. And so with that, talk about one of the components that we have looked at is the vents. And with our ember generators, we're able to expose the exterior of the building to embers. And this is that ridge vent area that was highlighted in the yellow. This is up in the attic looking into that. And we can see the accumulation of embers basically getting through the vents. And I'll tell you a little bit about the background to this experiment. This vent was actually a plastic ridge vent, which in California is not allowed. But it was a plastic ridge vent that met the Miami-Dade in Florida requirements. And so why all this matters, to kind of, again, tie it into this wind and multi-perils, is Miami-Dade has this baffling requirement that is intended to reduce, not entirely prevent, but reduce water intrusion of water droplets. And that baffle can have a similar effect on embers. We see it doesn't prevent all of them from coming in, but it does prevent some of them. Now, one of the things that you don't see in this video clip until the end, and it's on a loop, and it's in the bottom of the image now, while that baffling can have some effect at reducing embers getting in, not all of them, but some of them, it can also capture debris. And that's what we actually simulated on the top side here. We kind of sprinkled in some pine needles into the top side of that ridge roof, which would be very typical, very common for homes that are surrounded by trees overhanging. And even if you don't have trees overhanging homes, and we've seen in these wind events how debris ahead of the fire front, in the same way fires can transport embers, they can transport non-burning debris. And we've heard instances of, people clean off their roofs and you have a big wind event, not a fire event, and it takes almost a day to clear the debris off the roof. So with that debris in the vent, the ember then ignites that debris. Again, this is a plastic vent, which wouldn't be allowed in California, but the difference is embers can not only get in through the vent, they can ignite debris that's accumulated on the vent, maybe in the gutter, and the subsequent flame from that, in this case, melting through or continuing to burn, maybe melting some of the asphalt shingles, or maybe getting to the underside there and igniting the structure. So, that's kind of walking through the process of showing this video here, showing one component, the vents, but, how it plays an important role in its susceptibility and what we can do, making sure that we have vents clear of debris, using non-combustible and not plastic vents to begin with. Thinking about ember resistant vents. So, right, this has the baffling for the water intrusion resistance, but there are vents specifically designed and tested to resist the entry of embers. Looking at another component, let's look at the decks. Talked about how, decks can accumulate debris underneath of them. If debris underneath of them ignites, we can see a scenario, and I know that this video probably isn't playing very well over the stream, so I'm just going to pause it here and not show the video, but I think it's paused at a pretty timely image in both of them. This is a side-by-side image showing the some testing done in the chamber. On the left-hand side, both of these decks have a redwood walking surface. On the left-hand side, we have a deck constructed with a metal substructure. So you can think of the joists that kind of provide the structural support, the posts that would, keep the deck elevated. Those are metal and non-combustible. And with that underdeck fire scenario, we were able to ignite the underside of that walking surface. It was redwood, but it's not nearly as intense of a fire as if we look on the right-hand side. This is the same size deck, 6 foot by 6 foot. It's in the same kind of experimental condition, just in the chamber with that realistic gusty wind that Faraz was talking about. The difference being on the right-hand side, the substructure of that deck is also made of wood, which is a very common construction technique for building wood decks. It's not only 2 by 6, I think 2 by 6, let's call it 2 by joist and post. And so that underdeck fire scenario, just some accumulation of debris that ignites from embers falling through creates this underdeck fire scenario. That underdeck fire scenario now doesn't just have the bottom surface of the walking deck, of the bottom surface of the boards, but it also has then that vertical orientation. If we think about fire behavior, vertical orientation really kind of helping to carry and sustain fire behavior of those joists burning. And again, with this kind of, still frame looking at like this, if I'm a homeowner or if I'm someone saying, all right, well, my deck might ignite from a wildland fire. And if I have maintained my underdeck area, there's a lower chance that I'll get this underdeck fire scenario, but maybe the wind carries the debris. In either case, if this deck is attached to my home, think about which one would have a lower intensity, less likely for the deck burning to ignite the structure between the two. And we see the kind of obvious benefits of building with non-combustible materials like metal. We talk about ignition resistant materials, but this is an important thing to think about. It's not just the deck that ignited and destroyed. If in both of these cases, the deck ignited, the deck create a pathway for the deck to then ignite the building, the home, right? And then we have that, okay, this deck ignites this structure that it's attached to, and then this structure is free burning. And then Faraz talked about the possibility of one home burning and then igniting a neighboring structure. And that's how we can get to these urban conflagration scenarios. And so now I'm just going to show a 60-second clip from some of those pictures that I showed there. This is about 7 minutes into a demonstration. This is a duplex structure, both sides of it being exposed to embers. Again, we've seen this picture before. On the right-hand side, we have gray gravel, embers landing in it, nothing for it to ignite. On the left-hand side, where we're seeing flames now, that is wood mulch, very common use mulch material. On that side, we have cedar wood shingle siding. So small fire on the ground. Faraz was talking about small fires, ignited the deck, ignited that shrub, started to grow into larger fires, spread vertically up the side of that home. This is a single pane window. So ultimately the fire broke the glass and got in. It's now spread up into that eave area. I talked about the interface of building components, what's on the ground, what's on the wall, where the roof extends beyond the edge of the wall, and kind of similar to one of those first videos that we showed of an attic fire from embers getting into that ridge vent. This would be a scenario where we might have an attic fire from flames spreading up the wall into the eave and getting to the attic. And I speak about this from my experience as a firefighter, not so much in the wildland urban interface, though I've done some wildland firefighting, but as a structural firefighter here in South Carolina, we talk about attic fires being extremely challenging. And I bring this up to mention, to think about, some of the extremely destructive fires that we've experienced, really over the past century, but most recent memory is thinking about, well, why couldn't firefighters put that out? So I'll tell you that in the best of situations, with full crews and all the apparatus and all the water supply, attic fires in the best of scenarios are challenging to fight. And so, in a wildland urban fire scenario where you likely have evacuations of maybe entire communities, you might have multiple fires, you have that high intensity radiant heat if it's close by, so you need appropriate PPE. I'm using this all to build up to say that, once fire gets into the attic, it's really challenging to extinguish in the best of scenarios. And so that gets into another scenario, thinking about homes being destroyed by wildfires. If they ignite, they're most likely to be destroyed. And this is confirmed by some of the damage analysis data that Cal Fire has collected in other jurisdictions, like the federal level, FEMA and others. We see wildfire as a basically binary damage mode. Either homes are entirely unaffected, a lot of that unaffectedness or a little bit of damage can be attributed to defensive actions from firefighters, or homes are completely destroyed. And again, without putting myself in the shoes of those firefighters, emergency responders on the ground, they may arrive to a house that looks like this, and with water supply, they could prevent it from becoming a pile of ash. But there's a certain level of triage. So yeah, that's just kind of to bring you into the research center to look into what we do at the lab. We appreciate your time and attention. As I mentioned, we put our contact information up here. You can reach out to us directly via email, or get inside some of our inner thoughts on Twitter. But with that, we just again want to thank the hosts, Michael and Stacy, thank the attendees for participating, and use the remainder of the time to address any questions. I saw at least one pop up in the question box there.
Thank you so much, guys, for both of you for your talk and that great review. And we're really glad to have a lot of time for questions here. So we'll start with the first one in the Q&A box, which is from Jeff Enos. Looking at your duplex video with the fire on the left, doesn't the fire itself create a low pressure as it consumes oxygen at a high rate? And that low pressure is filling with incoming air?
So yes, I would say the fire creates a low pressure, but I think maybe for us, you want to talk about it's like at the scale of things. In that demonstration, we were testing at winds nominally 15 to 20 miles an hour. Likely there are so many other pressure differentials that it's true if you looked at like a small control volume, there was a pressure differential, but likely the other factors like the wind speed played a more important role in fire behavior and fire spread.
Agreed, yep.
So there's a question here in the chat from Thomas Paulson. A recent fire, the coastal fire in Laguna Niguel, Southern California, destroyed 20 mansions last week. The chief stated he believed embers made their way into the attics of the homes. You mentioned plastic ridge vents are illegal in California. Are there any vents that are completely fireproof? Also, which building codes have been implemented based on the findings from your research?
Good question. Thank you for that, Thomas. So let me talk literally about the coastal fire. Yeah, so I actually had an opportunity to reach out to some of our contacts in California, and not talk to firefighters that were on the ground, but talk to people that were talking to firefighters on the ground. I saw that same statistic. It's hard to, in my opinion, attribute an exact ignition mechanism to why did a home ignite unless you were like there and saw it. Unless you saw the ember land in that bush and that bush ignited the siding and it spread upside and got into the attic. It's hard to tell. A burned down structure is a burned down structure. And that's one of the things that, we try to recognize the benefit of the lab of recreating that. The other reality is, while I described that scenario, that may not be the only ignition of that structure. That might have happened at the same time that embers were getting into the attic. And so there's this kind of multiple ignition points. It's all to say that I don't doubt the role that embers getting into attics might have played there. I just also want to recognize that while it's important to keep embers out of the structure with appropriate vents, ember and flame resistant vents, it's also important to recognize that there are other mechanisms that could have led those structures to ignite. The question about, how do we take the research that we're doing and integrate it and move the codes and standards world forward? Faraz and I both participate both at national level through ICC and NFPA and ASTM, and at state level, including California, building codes and standard test methods. So, we are actively participating in that process. Some of the underdeck fire stuff that Faraz worked on, maybe you want to talk about here. We're actually trying to take to improve the standard test method for evaluating decks. So Faraz, you want to talk a little bit about that, about the research and then how it is, hopefully going to change the standard test.
Yep. As I mentioned, like the two side-by-side videos, both of those decks are compliant with Chapter 7A. And we are working through the process of basically changing the standard to discriminate between these two. And that would be probably a real world impact of how we take our research here in the lab and implement that in the basically building codes. The other part of that would be the wildfire prepared home. Do you want to talk about that, how we take our research to up there?
Yeah, and so Faraz mentioned wildfire prepared homes. So it's kind of the translation of IBHS as an organization is research and communication organization. If you go through IBHS.org and find that somewhere, but there's a kind of communication or kind of, you know, putting something into real world impact that's Faraz used. So let me talk about this without too much of a plug, other than to say, you know, we have experience taking our research and acknowledging where building codes, which are minimum standard, aligned with the science, but there are instances where the science says, well, that may be the minimum standard. We know better, we can do better. And we have a program, the Fortified program, that homes and businesses can be designated to basically our standard, that say, okay, well, not only did you meet the minimum code standard for your jurisdiction, but you also met our standard. And that designation can carry weight. It can move things forward for the availability and accessibility of insurance. And so taking that model from the wind space, applying it to the fire space with wildfire prepared home. And a lot of the stuff that Faraz and I have talked about, our predecessor, Steve Quarles, has done, looking at the importance of individual building components, like the vents, like the roof covering, like the siding. One of the challenges is just the regulation and, you know, how it's controlled. The building code regulates the building, but we know how important it is what's around the building as well. And sometimes those hands can't talk to each other. So, you know, our designation is aimed to address that, looking at the building as a system and looking at the parcel as a system. So that's something that we're going to be rolling out this year. And, you know, I think is one of the interesting things. I actually spoke at one of the early career seminars for this group end of 2021. And one of the things that I talked about, you know, interesting for me in this role is getting to do the science and research things that, you know, is oh so interesting. All right, it's like playing a kid in the sandbox, but also trying to think outside of what I normally think are my strength and, you know, how do we apply this and seeing there's other side of it. So hopefully that answered your question about how we directly participate in the consensus codes and standard process space, but also how we, you know, from IBHS perspective, take it and package it to really have impact for homeowners and communities that need to use it.
Thank you so much. You know, there was a piggyback question, and I followed the Laguna fire and the coastal fire, spoke to some folks on the ground, and the piggyback question is actually about the size of the structures, but I'd also comment we saw very good defensible space on some of the structures that burned down, which I think is why they've highlighted, and I spoke to someone on the ground, embers, but it would be great to know where those embers actually ignited. And maybe someone has security camera footage they want to share. But I'll let you take this because I think it was Michael Wara from Stanford had commented the size of the structures could have contributed. I haven't really heard that before, so I'd love to hear your guys' take.
Yeah, I would say the size of the structure matters relative to the surrounding structures. If there is like a 3-story building surrounded by 1-story buildings, well, that does matter in changing, basically maybe blocking the radiation or changing the flame patterns near structure to structure fire spread. What did you say?
Yeah, no, I think that's the same thing. Maybe we can talk a little bit about building size and building shape affecting, you know, wind flow around it, and embers where they land in a bad way, but maybe water droplets where we want to get them in a good way.
Yeah. So about the water droplets and embers, both of them basically wind carry them in the same situation, right? They follow the wind vortices. Taller structures basically have vents up on the ridge or maybe in the attic area that the lighter embers that can travel further away from the ground, those can get into the building, but the shorter structures are not basically exposed to embers that can fly at that height.
Yeah, and I guess I was going with that to talk about Exterior sprinklers, it's a question that we get asked a lot. And I guess it was just kind of a lead in to say, if there was going to be a question, or maybe we'll just kind of get off the head, we talk about building material, building, construction of the material properties, but what about like more active things with systems? You think about sprinklers inside of a structure. Exterior sprinkler systems, I think are not new in this space. Exterior sprinkler systems used to spray water in the agricultural industry. We've seen a proliferation of these sprinkler systems being installed on and around structures with the idea that you activate the sprinkler system, spray water as the fire is approaching or right as the embers start to land or when it needs to activate, depends. And that is a mitigation. That's an active mitigation thing that you don't need a firefighter there to spray water. You just turn the system on. And then maybe I'll kind of summarize, say, right, embers get places we don't want them to go because of the wind, but also sprinklers need to spray water, but that wind can cause some drift and maybe doesn't get the water where we need it to go. So again, just to mention, plug some of the stuff that we're looking at now, looking at structure separation, looking at things, not just building materials, what can we do to existing structure, retrofitting like exterior sprinkler systems.
Thank you for that.
On the sprinklers, I know a lot of people oftentimes ask, like, can I just do this? And I wanted to make sure that if you are thinking about a sprinkler system, make sure it's not going to take from the firefighting efforts. So if it's connected to the municipal system, can actually take water away from where it's needed, take pressure away from it's needed, and it's assuming that it'll actually function when you need it to function.
Yeah.
So having, it be like gravity fed, backup source, its own cistern of water, if you are going to consider that, and also to not rely on that as the only method. Sorry, I have to think about sprinklers, so I just wanted to throw that in there for talking about
it. Well, that's a great point, because I didn't mention that, Stacy, but it's all very important. And, we talk to people like you, and now I know you're interested, so you're going to be on one of our contact lists about those other things. We're trying to address parts of the problem, which we feel like we uniquely can. There are bigger pieces, water supply, activation, but this is a project that Faraz has had even if you had infinite water supply and all of those things solved, are you actually spraying water where you need to, where you expect to, and is it getting it wet in such a way that it's going to do something meaningful? As a slight aside, and to the kind of point you made there, Stacy, I would say, from what I understand, installing one of those systems is expensive. And I would say the money spent doing that exterior sprinkler installation can likely be spent doing twofold over things around the structure and material properties of the structure that I don't know if I want to say this, but I'll do it anyway, provide more benefit or more, confidence in the benefit. So thank you, Stacy, for bringing up that other part of it, because it's important, and we get to talk about that too.
So I'm going to jump in the questions a little bit because this lines up just with what you asked earlier about the size of the building versus proximity to next to the building. So you answered about the size. The question is the proximity more important or the size? So distance to the next building. From Steve Quarles, who we...
Yeah, you got us, Steve. That's a difficult question to answer. I think the science is not there to say which one is more important. If I want to choose between, I would say what is around the building basically defines the exposure, the thermal exposure to the building, and that would matter more, because at some point, that would the thermal exposure would exceed the tolerance of any material, right? And that's my train of thoughts on that.
Yeah, I agree with that. And then add a little nuance, thanks, Steve, is the size of the structure, when we're thinking about suburban communities or kind of residential communities, the size of the structure on a fixed parcel size is not entirely disassociated with the proximity. So if we have a fixed parcel size, a larger structure is going to be closer to those parcel limits, that setback distance. And then if you have a neighboring structure that's also very large, you're then going to have a small separation distance. So they are kind of tied with each other. But as Faraz mentioned, this is a question that we get time and time again from people that understandably are having to make decisions about it. We want to support that, but through the scientific method and the experimental process, we need to work up to that. So we'll be sure to give Michael and everyone a heads up as that research progresses, so you can follow along live streams and reports and whatnot.
Great, thank you. So there's two questions on vents. One is whether the ridge vents here in California are open cell foam and if those are resistant to embers. And the other, more generally, what do you recommend for hardening existing ridge vents?
So open cell foam, I think, I don't know where it falls on the ember resistant classification officially, but I'll give my 2 cents on it. I think it would fill the void. So you may not have large embers passing through a vent with open cell foam. But I would say, and again, I don't know this, but depending on the chemical composition of that open cell foam, might be a similar scenario as when we put some pine straw in the vent. The embers might land on it, and enough of them piled up together might be enough to then ignite that foam. So let me jump into the second question. How do we retrofit ember resistant vents? And again, credit to Steve, who we know is on the webinar today, did a study looking at exactly if we have metal mesh screen, which we know cannot prevent but resist or limit the size of embers to get through, and we look at 3 sizes, 1/4 inch, 1/8 inch, or 1/16 inch. What size mesh should we cover our vents with to be most ember resistant? So 1/4 inch mesh, pretty commonly used. The challenge is it can let up to a 1/4 inch size ember through, which a larger ember, more mass, has more ignition potential. 1/16 inch mesh only lets in smaller embers, but we got to see the opposite side of it. It can also accumulate debris and reduce natural airflow and then serve a purpose. If you keep your vents really clean, 16th inch mesh would be great because you're only going to let in 16th inch or smaller. We've kind of settled on in the middle, and this is was in previous versions of Chapter 7A that allowed retrofitting to install 1/8 inch metal non-corrosive mesh on your vents, and it's not going to prevent embers from getting in, but it's going to basically act as a filter. Only embers smaller than that are going to be able to pass through. And embers that small, smaller than 1/8 of an inch, are going to have less mass and less potential to ignite something. So that's a common practice that we talk to homeowners. I've done it myself in my home. It's a DIY project if you can get up into the attic, into the crawl space to do it, and it can make a big difference if you see some of the videos that Steve produced to show the difference in the best vent sizes and restricting ember entry.
Great, thanks. So there's a good question, which you guys might have the expertise about long-term ignition resistance of fire retardant treated wood.
Yeah, so we looked into this topic from different angles. Basically, gels, so let me start over. Coatings could be divided into different categories. One is pre-wetting material such as gels, and one is basically the materials that provide a thermal shield, like intumescent coatings. The latter group is basically treated or labeled as long-term treatments. Those are exposed to weather outside, right? And their fire performance decay with weathering. Our research shows that we tested 3 products commercially available in the market, and none of them showed any benefit after 1 year of weathering. And the research is published, you can Google it, probably find it. About the other side, pressure treated wood could be treated against weathering or fire. I am not aware of any product that meets both criteria. It's either weathering or fire performance. Well, wildfire might happen, but weathering happens all the time, and people basically choose the pressure treated wood against weathering and decay.
And then following along, there was another question from Jeff about whether you've tested water additives like gels or foams on the side of buildings.
Yes, we have. So basically, these materials are marketed as do-it-yourself type of thing. So there's like, when you buy it off Amazon, it comes with a spray, you can, and a nozzle, you can spray it on your home. There are a few safety concerns there. We do not recommend homeowners doing that because it gets clogged, you need to unclog it, and it takes a long time to spray a small wall. Because to manufacturers' recommendation, it should be 1/4 of an inch thickness. Putting that aside, if basically professionals wants to apply that, We saw that they don't adhere to all surfaces like windows. They just slide off because of their basically this dense material and it's like heavy. And in addition to that, they also go through weathering. And we saw that after, if we introduce them to wind, low relative humidity, after 4 to 5 hours, and this research is also published in Fire Technology, after 4 to 5 hours, they don't show any benefit against fire.
Thanks, guys. So I have another question, actually from a student in my wildfire class that just concluded, from Michael Milazzo. Has IBHS tested any structures that resemble old homes or buildings that exist in many rural areas? I think that was a good point. Has there been tests of, buildings up to code and not to code? And I think you have the answer there.
Yeah, so that's a really good question, Michael, and hopefully you did well in the class. I think it's a well-founded question, and I'm going to kind of answer it in pieces. All of the structures that we've tested here at IBHS, we have built on site. Now, sometimes we build it in April and don't test it until October. Sometimes we build it in October of 2016 and don't test it until 2018 and 2019. So there's some amount of aging, but I think the question that you're getting at, Michael, is probably more than like 2, 3, 5 years of difference. You're talking about a home constructed in the 1970s with materials and techniques from there being exposed in 2020 to a wildfire. And so while we haven't looked at that, it's an important part of it. And it gets into another layer to talk about, it's not just the materials, it's not just the design features, it's the construction, what's the best way to put it? Quality, but I'm not a carpenter or a constructor, so I don't want to, speak out of turn here. Other than to say that, small little differences matter. And I'll use an example that's been pointed out to me by our predecessor, won't name him again. But if you look at an open eave construction and you see the rafters coming out and you see the blocking, and that's kind of that 2x material that you see between the rafters. Again, not to call anyone out from a construction technique, but you might see some gaps where that blocking is supposed to butt right up to the rafter, but actually creates a gap. Now, that's not an intended vent from a venting purpose, so you might not think to put 1/8" mesh over that, but that little difference in the construction quality creates a vulnerability where embers can get in, where flames can get in. So all of that is to say, we have not looked at trying to build a home to 1970s building practices, though it's a really good question, and I'm going to ponder it some more. We have looked at kind of natural aging. Faraz talked about, some of the aging stuff that we've done for gels, the deck research he did back in 2018, 2019. We actually have some decks sitting out there in the field. You saw that in the picture. We're going to let them age for 5 or 10 years, so they're going to get the sun, the precipitation cycle, and we're going to test them. Maybe that addresses some of the questions that was asked in the comments, natural aging effect. So we do look at components, but just kind of logistically, no. But I think it's a good line of questioning and something that we should take into context when we think about, yes, we built with the same materials that might be representative of 1970s, but we were building 6 of these, and we have carpenters that have tools and techniques more modern than then, and the construction quality does play a role. It's not just the age of the structure, it's not just the materials. It is almost at a structure by structure, and almost maybe, you had one crew on Monday, did a really good job, and a crew on Wednesday, not as well. But good question, Michael, good line, thank you.
Thank you, guys. So we've got, I think, 3 questions lining up here before we finish. So the first from, I think it's Janique Allen, clarifying the recommendations for vents. What size? 1/16 mesh, 1/8?
1/8. 1/8.
1/8. Okay, great. And I'll just clarify, I think from the experiments, the 1/8 still let some particles in, but they couldn't ignite anything, right? Or they couldn't ignite cotton.
Correct. And same thing for the 1/16. I mean, an ember lands in that vent and it's larger than the 16th inch and it burns down until it's smaller. So you have some essentially ash in the attic. So something gets through, but it's the size of it and the mass of it. And, embers are important because they can ignite something. If an ember lands somewhere and it doesn't ignite something, yeah, you have to clean it up, but it didn't do the really bad thing that embers can do. So 1/8" mesh.
Great. The next is on aluminum foil reducing fire risk, and they noted the Sequoia National Park. And I'll first start off, that is not normal aluminum foil. The wrap they use on those historic buildings, it's like $40,000 for a historic building. That is expensive stuff with fiberglass layers, but take it from.
So yeah, I would categorize them the same way I put them in coatings, right? Coatings are preventing material and shielding material. These are basically shielding material that reduces radiation for the most part, or flame contact. I have a difficult time wrapping my mind around how we want to, in like a real wildfire scenario with 50, 60 miles an hour wind, cover a building with those, but theoretically they would work. Yeah.
Yeah, I think there's been a lot of research even published on whole home blankets. And yes, if you had 100% seal over the entire house, but if you have 20 minutes warning, how does one do that? And that's part of the problem. But maybe there are solutions, and there's certainly some problem areas we know about, like vents. So another question here from.
Sorry. I was just going to say that I was asking in the chat too about the vents. Could you cover your vents with some kind of shield as opposed to a mesh? I mean, I think aluminum foil was mentioned. Again, I'll say the same that Michael said. It's not just aluminum foil, but yeah, would it work on just vents if you were targeting a specific area?
I would say yes, and maybe instead of covering the whole house, it's a better strategy to kind of target specific vulnerabilities like vents. Let me throw another idea out there. We talk about how windows can be vulnerable if the glass breaks and it's basically an opening. So there are products available, roll down metal shutters or closable metal shutters. You could think about those, as Faraz was talking about, like as active thing. You wouldn't want to keep your vents covered all the time because you got to have airflow. But if you know fires in the area, if you have more than 20 minutes, as Michael talked about, and this is where it becomes harder to say, well, like how pragmatic is it? But let's assume you have 2 days notice. A good thing to do might be to, protect those vents and, better protect your windows. But I think, we think about that's the best case scenario. Let's not talk about the worst case scenario. Let's talk about kind of a lot of what happens in between.
You have 2 days, brush all the material away, staple some fine mesh, close your windows, do some of the basics. Yeah. Steve Quarles also added a note that Ashi Zhao, who was your advisor for us, evaluated that material and said that if the radiant heat is there long enough, it will delaminate. So it only works up to a point. And that embers passing through a 1/8 inch mesh can still ignite some finer fuels. There is a limit, but if you...
I was gonna say, that's the man that was in the attic doing it. So I take the word from him. And I just, hopefully I phrased that correctly, Steve. We just acknowledge the need to find the balance between only letting in small enough embers and maintaining your vents so they, in normal conditions, provide the functionality of letting air in and out.
Yeah, and if you don't, there's mold problems, heating problems. So you have to. So the last question, which I'll let you guys take, it's from Amber. How would straw bale homes with earthen plaster perform in terms of fire resistance? It's an innovative idea. I'll give my 2 cents. I think that the home constructed with that material could be constructed in a way that is wildfire resilient. You'd have to really, really limit the potential for direct flame contact, so managing the fuels around it very intensely. You'd also really want to limit the potential for embers traveling the short distances. We talk about long distance ember transport, but short distance ember transport, those larger embers can travel the shorter distance. So not only flames and radiant heat, but embers being produced by burning things around the home. And again, maybe that construction technique has benefits from a green perspective and an insulation perspective. The thing that I would say is it may not be
impossible, but I think it would take more effort and much more attention to details to address, because I can envision every one of the potential straw bales as a place where an ember could land and could ignite it.
Thank you so much. And, you know, seeing some of these comments, it's kind of interesting. Maybe someday there can be a resource that gets updated with all the tests for each particular type of vent, or, you know, all vents, all stuccos in this, because there's so much literature, especially a lot of corals and IBHS and others that were never published in the open literature, but are in reports and things that are technically open, but maybe a little harder to find. So I just want to thank you all for this great talk, and especially the discussion. Thank you all for attending and participating. And our next seminar is in about a month. And with that, thank you so much. We'll see you on the next time.
Thanks all.
Thank you.